All right. Now let's look at how to solve LP problems using the graphical methods. And the graphical method we just it is actually used, right, when you have two variables. When it's a two variable model. When it goes beyond two variables, it's very difficult using the graphical method. So let's look at, and this is what we do. These are the steps. You represent a given problem in mathematical form, and we have already learned how to formulate the mathematical model. Then you draw your x1 and x2 axes, what we normally call the x and y. So this is your x1 and x2. So that means we are looking at just two variable model. And not forgetting the non-negativity constraint. That means our graph will be just in the upper quadrant, right? That is upper quadrant, the right quadrant. Then we plot each of the constraints on the graph. Each of the constraints, that's what we'll be plotting on the graph, assuming they are equalities. Then plot them. Then after that, we look at what is known as the feasible region. We've looked at feasible solutions. So we look at the region in which we believe that the solution will fall in. And mostly the solution falls at the vertices of that particular region. We'll look at it shortly, quickly. We'll not waste any time. Let's look at the problem. That we know how to solve them. So it said that a manufacturer produces two products, Clank and Click. Now Clank has a contribution of 3 per unit and Click 4 pounds per unit, right? So the manufacturer wishes to establish the weekly production plan which maximizes contribution, and this is the production data that has been given. I have machine hours, labor hours, and materials in kilograms that are used to produce the two products, Clank and Click. And we have the total available units, right, in terms of either hours or kilograms per week. So that means you cannot go beyond that. And so far as we know how to formulate, so the first, now because of a trade agreement, sales of Clank are limited to a weekly maximum of 20 units. They are limited, right? You can't go beyond 20 units. And to honor an agreement with an old established customer, at least 10 units of Click must be sold per week. So for sales of Click, we can go beyond 10. But for Clank, the maximum is 20, right? So we want to formulate a mathematical model for these two products, and we've learned how to do it. So we can let x1 be the number of units of Clank and x2 number of units of Click. Now we want to maximize the rest one. Now where did we get this from? We were told that Clank and Click, Clank contributes 3 pounds per week, and Click contributes 4 pounds per unit. So we want to maximize the output, and that's what we want to do. We're maximizing output, and subject to these constraints. And for machine hours, 4 hours for Clank, 2 hours of Click, and the total hours per week is 100. That means you cannot go beyond the 100 hours in that order, and that gives us all these constraints. Now the constraint D and E comes from this, that the sales of Clank are limited to a weekly maximum of 20, and that of Click, right, should be at least 10 units. So that is what we have here. So x1 should be less or equal to 20, and x2 should also be more equal to 20, in addition to the non-negativity constraints that we know. So let's see how we plot this. And we are told that we plot the constraints. So for the first constraint, constraint A, we are given 4x1 plus 2x2 is less or equal to 100. Can you pause it? Plot this. We just change this. Assume that the inequality is an equal sign. So how do you plot this? If we assume, we can let x1 to be 0. So if x1 is 0, then x2 will also be equal to 50, right? And if x2 is 0, then x1 will be 25. Okay, so we've gotten the points 0, 50, and 25, 0 to plot. So that will give us the line for the first constraint. Then for constraint B, we have 4x1 plus 6x2 less or equal to 180. So we assume if x1 is 0, then x2 will be 30, right? I think I'm right. 180 minus 6 is 30. And if x2 is 0, what will be x1? That is 45, right? 45 times 4 will give you 180. So we have 0, 30, and 45, 0 to plot. Then let's go to constraint C. Constraint C, we have x1 plus x2 less or equal to 40. So if x1 is 0, then x2 is 40. Sorry. Then if x2 is 0, then x1 is 40. So we can plot the point 0, 40. Then, 40, 0. Then the other constraints, that x1 is less or equal to 20. That's a straight line, a vertical line, and x2 more equal to 10 is a horizontal line. So after getting this, we plot. Just plot the constraints. That. So let's assume. Can you go here? So let's. Will it be okay? Or I should clean?
It's okay.
It's okay. Okay. So this is your x1 axis and this is x2. So for the first constraint, we'll be plotting 0 and 50. So mind you, this is 0. So 0 for x1, then 50 for x2. So let's assume this is 50. So this is what we have, 0 and 50. Then the next one will be 25. So let's assume this is 25. 25 against 0. Plot 25 again. Then we draw, right? We draw a line. I'm not good at some of these things. We have this. So this is the function. This is the function 4x1 plus 2x2 less or equal to 100. So let's begin. Later we'll make use of the inequality. Then the next one, constraint. When x1 is 0, x2 is 30. So this is 50, 25. So 30 can be somewhere here. 30. We have this. Then x2 is 0. x1 is 45. So 45. Let's assume this is 45. So we draw. It's 45. So you can use your graph sheet to do this. Sorry, this inequality is 4x1 plus 6x2 less or equal to 180. Then the last constraint, x1 plus x2 equals 40. So 0, 40. So 40 and 40. So this is 40. Here. Another 40. 40 is from here. 40. Maybe I don't plot well. Okay, let's assume that we have this. Now, the other constraint is that x1 should be less or equal to 20. So we have 20. So let's say this is 20. S1. So x1 equals to 20. That would be a vertical line. Right. So this one is x1 less or equal to 20. And the other one, x2 more equal to 10.
So I do not write for the 40, the inequality for the 40. x1 plus x2 less or greater than 40.
Okay, this one.
Yes.
x1 plus x2 less or equal to 40, right? Then the x2 more equal to 10. And this is 30. So divide by this, so let's assume this is 10. So you have something like this. So the graph, I hope that it came well. Because we are not drawing to scale. Can be something, but we look at it. X2 more equal to 10. Now, let's see what we can use. We use the inequalities to determine the feasible region. So, for the first constraint, we are told that it should be less or equal to 100. It should be less or equal to 100. And this one. So, what we do is that we shade to less or equal to means to the left. So, let's shade to the left. When we shade to the left, like this, right? Less or equal to that. There we go. But mind you, it shouldn't go beyond. I made mine go beyond. Shouldn't go beyond the S1 and the S2 axis because of the non-negativity constraint, right? So it shouldn't go beyond. Mine have gone beyond, but it shouldn't be the case. Then the other one, this is the line for 4x1 plus 6x2 should be less or equal to. So this line should also be less or equal to. Let's shade vertically and see. That one too shouldn't go beyond that other like shade. Then we have this one. We say that x1 plus x should also be less or equal to. So this one too. Let's shade horizontally. Now you can see that there's a region that intersects all of them. Now the other two constraints, x1 less than 20. So that means we should go to the left of 20. We shouldn't go beyond 20. We shouldn't go beyond 20. So if you are not going beyond 20, this is where we are. And also, we shouldn't go, this is where we are. And I think we should go above 10. It should be more equal to x2 should also be more equal to 10. That means here, from here upwards. So let's see, from here upwards, I think we'll come here and this region intersects all of them. So I think we have something like this. A region like this to deal with. I think we have this region. Let me see if I in the blue marker can show whatever we have. We have a region that is bounded by these vertices or points, right? And we can determine this point. Now we know that this point, I think the blue is not helping matters. We know that this point will be 0, 10. Here will be 0, 30. This point, we'll have to determine the intersection of these two lines, right? Where the two lines intersect, what happens? We know that this will be 20 something, right? So when x is 20 along this line, where is this curve? Where is the equation? So when x1 is 20, we have 80, right? So 6x, so 100 minus 6x, 100 minus 6 will give us what? Give us some decimal values, and this one too, we find the intersection between these 2 points, where x equals to 10 and y equals to, so this point will definitely be 10 and 20. This will be 10 and 20. Sorry, 20, 10, 20, 10. Then you also locate this point. This will be 20, and when you substitute x1 equals to 20 in this point, what do you get? So, to give us something like this, yeah, we got something like this. And I think, yeah, somehow I think 1.5 there also. Yeah. So that's the region that we are talking about. I think I didn't write well, that's why it's like that. Okay, yes, something like that. Now, this is what happens. After getting the points, the vertices, you substitute the vertices into our function, right? Our function, and the objective function was given us 3x1, or we can say z equals to 3x1 plus 4x2. So when we make the substitution of all the points, let's see what we have. You substitute all the points. So we first substitute 0, 30. So let's substitute 0 and 30 and see what we have. So when x is 0, x1 is 0, x2 is 30. So we have z equals to 4 times 30, and that is
120.
120. Then you do that for all the points. Now we want to maximize. So the point that will give you the maximum, right? That will give you the maximum is the optimal value. So that will be our point. In this case, this one, I think 15 and 20. Okay, that means it's only here, to be somewhere here, rather. To be this curve. The point will be rather here. Or 15 and 20. Yeah, to be somewhere here, right? So this one will be out. So you substitute all of them, the one that gives the maximum. Right. So 15 and 20 give that. And the optimal, our optimal value is 125. Right. So that's it. Let's look at another example. This one, the problem has been formulated already. So we just need to solve graphically instead of 2 variables. Equals to 2x1 plus 3x2, subject to these constraints. So let's graph the constraint. The first constraint is x1 plus x2 is less or equal to 30. So when x1 is 0, x2 is 30. When x1 is 30, x2 is 0. So plot the point 0, 30, and 30 is 0. Then the second constraint says that x2 is more equal to 3. Right? That will be a horizontal line. And you have another one, x2. So this will, x2 is also less or equal to 12. That's also a horizontal line. Then x1 minus x2 should be more equal to 0. x1 minus x2 should be more equal to 0. So in that case, we'll be plotting x1 should be more or equal to x2. Or x2 should be less or equal to x1. And so we know that when x1 is 0, so when x1 is 0, x2 is also 0. Okay, so that we'll be looking at the 45 degrees line through the axis, through the point 0, 0, the origin. And the last one is x1 should be less or equal to 20. So let's look at how we plot this. Marker is sinking. This one is good. But this is a new marker. let's start with these constraints. X2 should be more equal to 30. So let's assume that. So let's assume is it more equal to 30? Oh, sorry, more equal to 3. So let's assume this is 3. 3, so, wow, and 30. 2, 5, so 3 meters. So we look at this line. This is x2 more equal to, so we should go above that line. Then the next one, x2 should also be less or equal to 12. So if this is 12, this is 3, let's assume this is 12. So less or equal to 12. So x2 less or equal to 12. So we know that our feasible region should be bounded by 3 and 12. We'll be within that region. Then x1, let's come here first. x1 should be less or equal to 20. So if this is 20 and this is 20, so x1. So x1 should be less or equal to 20. That means to the left. So that means we're dealing with this region. Let's continue and see. Now we are told that x1 minus x2 should be more equal to. So when x is 0, and that's order. So we're looking at something like a 45 degrees line through the origin. I hope it's 45 degrees. Let's assume. So this one, x1 minus x2. And we are told that it should be more equal to 0. So positive, upwards. So that means we are at the region. Where are we now? We are here, right?
Mm-hmm.
We are here. But here, this region will be less than 20. We are less than 20 now. So now we are here. Now let's look at the first constraint. The first constraint, we have 0 and 30. So let's assume this is 30. 0 and 30. And the other one is
30 and 0.
Because we are not drawing to scale, we might not get what we want. But later we look at. Right. So if it is to scale, that means, and then that should be less or equal to. So if we drew to scale, that means we're looking at this region. If it was to scale. Right? More like a 5-sided figure. Look at this. So we're looking at this region. So this will be a feasible, and the vertices will be the points we're using to determine the optimal value. Let's quickly go to, because we are not drawing to scale, it's very difficult obtaining these values. But you can draw with your graph. That's what you're supposed to do. So you get a graph sheet and you draw. Oh, sorry. Go forward. Let's see. So I think we are similar to. Okay, there's one constraint. Okay, so this is more equal to. Oh, sorry. So should have come here, right? If it is more equal to, this line should be more equal to, so we have been here, right? To the left, right?
Mm-hmm.
We have come here. So where will we be? Somewhere here, right?
Yes.
The region is used like this. Okay. Should be more equal to, not less or equal to. Less means we shape to the left.
Opposite to the right.
So, sorry, it will be this rather. But we are not drawing to scale, so it's different from what we see from this line. So let's look at. So these are the vertices for the optimal solution. We have 18, 12 here. Let's look at the other. The other vertices are 3, 3,
12, 12.
18, 12, 20, 10,
and 23.
and 23. So you substitute this into the objective function, right? You substitute these values into the objective function was given as z is equal to
2x1 plus 3x2.
3x2, right? So you substitute these points
A, B, C, D, E, and F, and E.
Yeah, you substitute them into the objective function. This function z, the one that gives the maximum value. I think the maximum value is 72, right? That's for point C.
Yes, 18 and 12.
So our solution is x1 equals to 18, x2 equals to 12. That will be our solution. Right. Okay. Thank you very much.